Okay. So last time, okay, let's start. We have a lot of work today. Okay. So last time I explained how can you design a sequential circuit for a sequence generator. Okay. So here I told you what I did last time was here if you have a sequence generator, I explain sometimes you have only one output out of this sequence generator. For choose the input of this sequence generator is a clock, right? So we have a clock here. Okay. So sometimes you can, in some example, and that's what we do in the next week for the first part of the project. You have only one output here. For example, this output, if the sequence, for example, 1001, this is a sequence I want to generate. So what should happen is, so if this is the clock, so in the first cycle, you will see number one. So you get number one in the first cycle, which is this one here. Okay. Second cycle, because every clock, every edge, okay, either it is positive edge or negative edge, depends on what kind of flip-flop you are using. Okay. For example, if it is a positive edge, so in the next clock, you will get 0, which is actually this one here. Okay. And then same thing again here. Oops. Where the change happens at the positive edges, okay? Same thing here, changes happens here, okay? Now, in next clock, you will get this bit here, so, okay? Then another 0 here. And then after that, you will get this one here. Here. And then this sequence here is repeated, okay? So you can see the sequence is 1, 0, 0, 1. Every bit is gonna last for one cycle. Okay. So the coming project, if you want to visually, if you want to see this the sequence, you have to make the clock very low. You know what I'm saying? So for example, if I connect an LED here, if I connect an LED and I want to visually, I want to see for sure you need to put resistance here, something like. So visually, if I want to see the sequence, so the output is 1, I want the LED to turn on, 0 turn off. So if you make the clock very fast, you will see the LED on all the time. Okay? Because your eyes cannot, our eyes cannot capture very rapid changes. Even the hardware itself, like LED cannot turn on and off very fast. You know what I'm saying? So that's why visually, if you want to see it, if you make this the clock 1 hertz, that means this one is gonna last for 1 second. 1 second, so every bit is gonna last for 1 second. 1 second you can notice it, you can make it actually half hertz if you need, or less than 1. Okay, anyway. So also I explained how can you make, also I can design a sequence generator. Same thing, we have here a clock, and I can have 2 outputs. I can have 3 outputs. I can have 4 outputs. This is something you can design. This is what I call the counter. Okay. For example, I can design it so that it has 2 outputs. In case of 2 outputs, I'm gonna see. For example, if it is a counter, so 0 and then 1, 2, 3, and then again 0. So this is the sequence gonna be repeated again. 0, 1, 2, 3, and so on. So every clock, you are gonna see 2 outputs every clock. So if I want to do something like that, so I'm going to put this one A node A1. I think I'm in the report of the project, I'm asking you to draw a timing diagram, something I'm doing right now. Okay. So here you need to show me if you have a block this way. Again, as I told you, changes happens only at edges. Okay. For example, if you work on positive edges, so only a change can happen here. Okay. So here is this. Oops. Anyway, the track, which one? I think I missed the picture. Anyway, so it should be at positive edges. Okay. Anyway, so this time you have, I have to see here A node. A node. You can see here A node is actually 0, 0, 1, 1. So I have to see 0. Then next time, next state 0. And then I have to see 1, and then 1. And then this pattern is repeated. This pattern is repeated, 0, 0, 1. Okay. For A1, I should see 0, 1, 0, 1. Okay. So it has to be 0, 1, 0, 1, 0, 1, and so on. This pattern is repeated. Make sense? Okay, so here we output two bits. Okay. And as I told you, this is something you can design. It doesn't need to be a counter. Okay, it can be any random sequence. For example, after 0, 0, I want to see 1, 1. It can be any sequence. Got what I'm saying? This is something you can design. Also, last time I told you I found the mistake here. I think this one was 1. I made it 0. This one was 0. I corrected it to 1. So I corrected this one. And so I already posted. I sent you email about that. So I updated the slide to correct this one here. Okay. So this now gonna change A0, A node or A1, but it's gonna change Y. So here when I calculated Y, I found Y equal A node exclusive always A1. This one. Okay. One more thing I explained last time, we need to today. Last time I explained, sometimes the design is more, and I told you test in the coming test, I will ask you, I will give you a circuit, I will ask you, is this circuit more or milli model or milli model or more model? How can you know? Very simple, very simple. If the output of the circuit is actually only function in the state, like this case, so this is more. So it's not functioning the input, but it's functioning the state. You got what I'm saying? So in this case, the input, it is used just to change the state from one state to another. So X can control if an existing state. When X is 0, for example, I will come here, X is 1, I will come here. But X does not have impact on the output. The output only is a function in E0 and E1. In 0 and E1. And that's what I noticed here, by the way. So here, when I took this Y here, I tried to simplify it here. The output doesn't have X. So the output is only A node A1 because this is more model. Okay, guys. In milli, okay, if for example, if X here, if X is the Y, I need X to generate Y. This is a milli design. Okay, guys, any questions? So what I will do today is I will teach something like last time, but I'm not gonna teach sequence generator. I will explain how can you make a sequence generator. Okay, I'm gonna explain today sequence detector. So sequence detector, for example, I want to detect the sequence 1, 1, 0, 1. Okay. So here I have input and I have out. So every time here, if you detect 1, 0, 1, okay, after this one here, for example, if I get 0, so only 1, so since the output is 0, okay, because the output should be 1 when this sequence is detected here as the input, okay. So now 0, okay, so still the output is 0. But now, because I already have 1, 0, 1, the output here should be 1. Okay, so here I have a circuit. This circuit has an input, and it has out. This output can be 0 or 1. The output should be 1 when this sequence is detected. Okay, when you detect a sequence. Okay, and this is actually the second part of the project, and you will do it. So the project, as I told you, it has two parts. One part is you generate a sequence. The second circuit should actually detect this sequence. Okay. There is something here, so I'm going to teach how can we design a sequential circuit to detect a sequence. Okay, you will see similar to what I explained last time. We have number one, I have to start with the state diagram, and as I told you last time, this is the most difficult part. Once you do the state diagram, after that everything is going to be systematic, as we did last time. Okay. Also, last time I explained how can you design using G flip-flop. So today also I will show you how can also use G flip-flop and also GK. It's not a big deal. It's also the same idea. Okay, you will see today. Okay, but there is something here I want to bring to your attention, which is when I design this. What is it? So when I design this sequence generator, I can design it in two different ways. Look here, look the difference. Two different ways. One way you call it overlapping, you allow overlapping, or actually you don't allow overlapping. That's a design. That's whatever you want. But you will see right now, it's really interesting. It's just a small change in the timing diagram. So if I just change the arrow, you will see when I do it. Okay, if I change the arrow from this state to this state, it becomes overlapping. If just I change it from here to this state, it becomes non-overlapping. Okay, but here I want you to understand what I mean by overlapping or non-overlapping. This is the design. Whatever you want, you want a sequence generated to be overlapping or no overlapping. So overlapping. Let's start with no overlapping, non-overlapping. So in case of non-overlapping, look here. When I have 1, 0, 1, okay, so as I told you here, we're going to output 0 because I did not detect the sequence yet. Here, I'm going to output also 0, but here, I'm going to output 1 because now I got the sequence. Is that okay? Now, in order to detect a new sequence, the new sequence should be 1. I need to find a new 1, 0, 1. That means this is where the word overlapping came from. So this one, the one here, cannot overlap between two different sequences. You got what I'm saying? That means, look here. So if I receive 0 here, I'm gonna get here 0 because if you look at the last 3 bits, it's not the sequence. But if I have here 1, look here. Also, I will get 0 because the last 3. Because I don't allow this sequence is already done. I don't allow overlapping. Overlapping means this one should not be overlapped in 2 different detections or 2 different sequences. Okay, so here in this case, I will get 0. However, someone can tell me, look, but here there is overlap. That's what I'm saying. Do you allow overlapping or not? A part of this sequence can be in two detection or not. Okay, so if you don't allow, so here I'm gonna get 0 here. Okay, but actually if you allow, actually this is the main difference. So here I'm gonna get 1 in case of overlapping, allowing overlap. That means, guys, here in case of non-overlapping, I have to receive a new 1, 0, 1 again in order to give you 1. You got the difference? Okay. But here I can allow overlap. That means if it is 1, 0, 1, okay, that's the sequence. I give you 1 here. But if I give 0, 1, yeah, I allow this a part of the sequence can be 1 bit or more, a part of the sequence to overlap. So here also I'm going to give you 1 again. Okay, it's up to you. You understand this design? It's a small change in the time in the state diagram. Okay, again, you will see right now. But for now, I want to make sure you understand what I mean by overlapping or no overlap when I detect the sequence. Any question? If you don't understand now, you are not gonna be able to understand when I explain it in details. You're just making a definition. You got what I'm saying? You understand what I mean? So here, in case there is no overlapping, that means 1, 0, 1, I have to get a new 1, 0, 1. Okay? It doesn't need to be 0 here. It can be like 1, 0, 1 and then 1, 0, 1. Yeah, okay. Any questions? So every time you detect a sequence, you are gonna make 1 here, output 1 here. Okay, let's give you the details. How can you make it? So, as I told you, we start. This is the most difficult part. How can you make the state diagram here? Okay. So, by the way, I added also here, there was, I think, 2 examples here. I added 2 more, I added 1 more example. So here, I updated the slides to add 1 more example here, okay? Just to understand this part better by adding more examples. Anyway, so let's start here. I wanna look here the problem description. I wanna detect a sequence of 3 or more consecutive ones. You see the sequence? 3 or more consecutive ones. Okay, that means, look how I'm making it here. Okay. I detected 0. Okay, output is 0. I did not detect these 3 consecutive ones. I detect 1, output is 0. I detect 1. Okay, output is 0. I detected 1, output is 1. Make sense? Because the last 3 are ones. Okay. I detect 1 again. Okay, so now I allow overlapping. I allow overlapping. Why? Because when I here, I got 1 here. Because you allow overlapping here. Okay? Because the last 3 bits are 1. Okay? Same thing here. The last 3 bits are 1. Same thing, the last 3 bits are 1. Because you allow overlapping. If I don't allow overlapping, that means after 1, 1, 1, I will get 1 here, output, because I detected 3 consecutive ones. Okay? But no, sorry. Here I'm not asking you. What I said is correct, but it depends on what you want to do. Here, guys, I'm not asking you to detect exactly 1, 1, 1. I didn't ask you for that. Okay, I asked you for 3 or more. Okay, so here I'm asking for 3 or more. So it's not. So 4 is okay, 5 is okay, 6 is okay. You can understand. I'm not asking you for exactly a certain sequence 1, 1, 1. Okay, if I ask you for 1, 1, 1. So here what comes up is a point I explained about overlapping. So here you have 1, 1, 1. Okay, I will give you 1 here. But I need to have a new complete sequence in order to give you other one if there is no overlapping. But anyway, so here what I'm saying here, at least the 3. That's why I got here 1. The output here is 1 because the last 3 bits are at least the 3. Okay. Here I got 0 because the last 2 bits are 1, only 2. At least the 3. Here it is 4, it's okay. Here it's how many ones we have? 1, 2, 3, 4, 5. That's why I have here 1. We have 6 ones. Okay, at least the 3. Now, if you come here, if you look at the last 3 bits here, okay, so I got only here I got 2, so the last sequence here is only 2 ones. Okay, also here I got 0. I got 0 because if you look at the last 3 sequence, we have the number of ones is actually less than 3, and so on. Here also 0 because we have here the last 3 bits, we have 2 ones. Here I got 1 because the last 3 have 1. Okay. You understand what you want to do? Now, how can we, again, the most difficult part is how can you make this diagram? I will show you how can you make it. Okay, look here, guys. So here I wanted to take 1, 1, 1. Okay, at least 3 can be more. I will show you now how we can make it. Okay, the first thing you need to ask yourself how many states, how many states you need. That's what you need to think about. Okay, so I'm gonna make one state here. State, for example, state 0. I should be here in this state if the last bit I received is 0. Okay, if the last bit I received is 0. Okay, now I'm gonna move to another state here. If I received after 0, I received 1. So every time, and this state, that means the last bit is 0. Every time in this state, that means the last state was 1. Okay? And then when I come here, okay, so it should be 0, 1, 1. When I come to this state, 0, 1, 1. Okay? The last, if I receive 1, okay? So here I'm gonna say 2, finally 3 here when I receive 0, and then 1, 1, 1. So every time I come to this state, what it means, every time you come to this state, it means I already exceeded 3 consecutive months. That's why we have here history. You can memorize what happened in history, because this is the main thing in sequential survey. What is the history here? Very simple. Here, when I'm in this state, that means I received 0, 1, 0, and then 1. Okay? When I'm here, that means I received 0, and before that, I received 1, 1. Okay? I will give you more details. But now, let's see how it works, guys, here. Okay? Number 1, I assume here in the very beginning, I received 0. Okay? 0 means I will be here in this state. Okay? Now, what if after 0, I received another 0? What should I do? I'm gonna loop here. So here I'm gonna loop here. So here x is 0 and y has to be 0. Okay? So if I receive 0, I'm gonna loop here. So as long as I'm receiving zeros, I will loop here. And as long as you are in this state, that means the last bit is 0. I'm not gonna start counting for the sequence because the sequence didn't start here. The sequence has to start by 1 because I'm looking for 1, 1, 1. Okay? So every time you have 0, I'm gonna just stay here. I'm not gonna start counting. Okay. Now, what happens if I receive 1? Okay, if you receive 1, so I'm gonna move to this state here, and still the output is 0. That means your sequence, I got only one bit from the sequence. Is that okay? If I receive another 1 here, it will come to here. That means now I got the second bit of the sequence. Make sense? If I receive 1 again here, I will again the output is still 0. Here the output is still here. If I receive here, I receive another 1 here. Okay. So here, here this one, and then I will output. You will I have here 1. So and then I will move to this state. So now I received 1, 1, 1. As you see, I want to make it simple, guys. Look here. In the very beginning, I'm in this state. I have 0. I have 0 in head. So the last bit was 0. When I receive 1, I'm gonna move to here. Second one, move here. Third one, I will move to here. So the only way to come to this state is by receiving 3 ones. Make sense? Okay. So here, once here I wanna design this circuit using more design. Okay. I will design again using melee, but you will see the difference. Okay? So here using mode here. So here in case of mode, the output only depends on the state. So as long as you are in this state, so I'm not gonna put the output here. You know, in case of mode, usually we put the output with the state because the output only depends on the state. So here, always if you are in this state, the output should be 0 because I only received 1, 0. Here, always if you are in this state, so the output here has to be 0. Okay, so I'm not gonna put the output here. Also, if you are in this state, because I didn't receive the sequence here, the output is 0. Once I come to this state, that means I received the 3 ones, means the output has to be 1. Again, the only way here, I'm starting from here, okay? First is the input is 0. The only way to move from here to here is when you receive 1. To move from here to here, receive another 1. Move from here to here, receive another 1. That means if you are in this, there is no way to come to this state unless you receive the 3 consecutive ones. That's why once you are in this state, I'm gonna output 1. I already received. Okay? As you know that in this state diagram, I have to consider the 2 cases for each state here. I have to consider the 2 cases, if it is 1 or 0. Okay. So let's think about it. If I already here, if I'm here, that means I receive 0, 1. Okay. If I receive 1, I'm gonna proceed the next state here. Okay. What if after 0, 1 you got 0? Okay. What should I do? You have to move back to here. So here, that means this is if the input is 0. So after here, after 0, 1, 0, 1, I received 0. So I have to move to the beginning again to start counting again for 3 ones. Make sense? Okay, let's look at this one here. If I come here, that means I receive 0, 1, 1. There are 2 cases. Maybe next one is 1 or next one is 0. If next one is 1, I will come to here to this state, and once I in this state, that means I already received the sequence. Okay. What if I receive 0 here? Okay. That means I need to start the count. I need to start over again to count for 3 ones, because I'm saying that I received 0, 1, 1, and then 0. That means I have to come back to it. Okay, so here if it is 0, I will come back to it to start the counting again for 3 ones. Okay? If it is 1, I will come to here. Okay. Again, you think about this one. Now, if I come to this state, that means I already have 3 ones. Is that okay? Again, there are 2 cases. Either next one is 0 or next one is 1. What if after you received 3 ones, I got 0? I have to go to this one here again. 1 to start counting for another, 3 ones. To make it easy for you. Always, if the last bit is 0, you have to be in this state. Always, if the last two bits are 0, 1, you have to be here. If the last 3 bits 0, 1, 1, you have to be here. Okay. Okay. Now, the other case, after receiving 3 ones, I got 1 more. What should I do? Yes, I have to look here and output 1. By doing that, that means if I receive 1, 1, 1, okay, I'm gonna output 1, and then here, if I receive another 1, I will stay in this one here because I'm allowing overlapping. Okay, so if you are here in this state, I will reduce because of this one here. I will reduce another 1. So as long as you receive 1, 1, 1, 1, you are gonna continue in this state. Any questions? I will give you another example. I know it's a little bit tricky, but I will give you another example. But let me check if I made it correctly. Okay? I just used my memory or it will be embarrassing. I think it's correct. I think so, right? Yeah. Yeah, it's correct. It's the same thing like this. Okay. Yes.
In the timing diagram, you used 0 as the first input. Will it still do the same if the first input is 1?
That's a good question. Yeah, we have here, we assume the initial. Yeah, we assume this is the initial state. So once you start, you come to this state. But regarding your question, if we start, it depends on what value for it. You should have some initial value for the flip-flops. That's why you need initialization. So the question here is, in the very beginning, you assume you are in this state, right? Because this is the initialization I will do. That is why in the flip-flops, we have 2 special inputs for initialization. One is set, one is clear. That means before running the circuit, you have to clear it first to make sure in the very beginning you are gonna be in this state. Because your state should be controlled by the values of the flip-flops you have. Remember, these 0, 0, these are the values of the flip-flops, 0, 1 are the values of flip-flop, and so on. That's why we assume this is the beginning. You always assume this is the beginning. So in the very beginning, you have, because if this is your beginning, you will start from here, right? But usually we assume you need to do initialization in the very beginning. Yes.
I was talking about the inputs. Like
Yeah.
you started as 0 and then 0, 1, and then 0, 1, 1, and 0, 1, 1, 1, and then it would continue as many ones as you added. But
So in the very,
did you start as 1 as the first input?
yeah, you can. No, you can. You can, but again, we agree in the very beginning, I'm gonna clear the flip-flops. That means I'm here in the very beginning. Is that okay? That's the very beginning. And then after that, what in the very beginning I receive 1, not 0. Okay, I will move directly from here to here. And then I will start counting with the sequence. Will be correct. You got it? Okay. So let me tell you something here important. You will understand better. I give you more example. I know this little bit tricky, but I give you a lot of examples to understand. Look here, guys. I don't use the design here. This is actually more design. In case of more design, if you sequence in 3 bits, like 1, 1, 1, okay. So actually, how many states you have? So the number of states should equal to n plus 1. where n is the number of bits you have in the sequence. This is if you use more design. But if I use mealy design, as I will do right now, if I do mealy design, actually number of states equal to only n. Okay? You will see right now. So what I did here is more design. How can you tell if this is small or not? Very simple. You can see here, guys. This is a very smart thing. You can see. Always, if you are in this state, the output has to be 0. There are sometimes, as you will see in case of mealy, this is the difference between, so here in case of more, always, if you are in this state, the output always 0 or 1, whatever. Always, you have the same output. However, in other, here I'm talking about any state. However, if it is mealy, it may happen that if I'm in this state, okay, maybe here 0 and 1, and here 1 and 0. So maybe here the output will be different. Okay, so this will be mealy. So if the output only depends on the state, that means if I'm in this state, always the output is 0 or 1. Okay, regardless what is x, so this is more. However, here in the same state, it depends on x. If x is 0, for example, I will get 1. X is 1, I will get 0. So now it's not, for the same state, I may have two different outputs. Depends on x. So now it depends on x. Okay, this is me. Okay. You will see again. So here, because I designed here in this circle, I designed it to be mode. That's why I told you in case of mode, number of states equal to n plus 1. N is the number of bits in the sequence. In case of mealy, a number of bits is equal to n. Okay. That doesn't mean mealy always better than mode. You know why? Because mealy has a problem, as I told you before. Mealy is not synchronized. Because the output here, you have a combinational circuit, and then you have the output 1. The input of the combinational circuit are the states, also x. So once x changes, the output will change immediately. That's why it's not synchronized. The only way to make it synchronized is to synchronize x. X should not change at any time. X has to change, should change only at the edges to make it synchronous. Is that okay? But anyway, so let's see if how I can modify this design. How I can modify this design to make it mealy instead of more. Okay. Also, before I do that, okay. So here, guys, we allow overlapping. Okay, let me look here. When I come to this state, here, that means I received 1, 1, 1. Okay, I received 1, 1, 1. Okay. Now, if I don't allow, that's why here, if I receive another one, I allow overlapping. That means I'm going to take the last 3 here. That's why I have this arrow here, this one, to allow overlapping. Is that okay? So when I receive, after receiving 3 ones, when I receive another one, I will look to here and then I will output 1. The output will be always 1. Okay. If you don't allow overlapping, that means 1, 1, 1, I will get here 1. And then I need to receive a complete new sequence. I have to have 1, 1, 1, sorry, 3 ones to get another one here. Look at very simple, it changed. What I will change here, guys, is, can anyone tell me? Okay, so look here, guys. Once I come to here, I already received 1, 1, 1. Okay, I'm happy. If I receive 1 after that, here will come the point of overlap. If I receive 1 after that, if you change the design so that I'm gonna come to here after I receive 1, please come to here to start the counting over again for 3 ones. This way it is not overlapping. So instead of this here, that's why I mean, it may be in the beginning it maybe looks difficult, but when I give you more example, you will understand it better. But you see, it's very interesting. If I just change this arrow from here to here, now it becomes non-overlapping. That means, okay, just give me. So here, now it's non-overlapping. That means after I receive 1, 1, 1, okay, so I have to come to state 0 to start counting again for 3 ones again to come to here. Okay, so again, if you just make this arrow this way, that means after receiving 1, 1, 1, if you receive 1, please give it to give me 1. Okay, but or I can say after I receive 1, 1, 1, please go to the initial state again, okay, to start counting for 3 ones. Yes,
Would you need to go, if you get a fourth one, would you need to go to the top right bubble?
here to this one here.
Yeah, because otherwise you would get four, when you get 3 ones, you'd be at the bottom.
That's a very good question. Let's think about it. That's a very good question. Let's think about it. It's, again, this is design. You need to think. So your question is that why I don't move to here? Okay. If I move to here, what would happen if you move to here? Okay. So in this state, that means I have already received 1. I'm looking for 2. That means you are gonna make overlap for 1 bit. You got what I'm saying? So I need 2 more. So once I receive 2 more, so if I move from here to here, okay. I'm sorry, you are right. You are right about this one because I received already. Okay, you are right. So what should happen here? I'm sorry. Yes, you are right. So I have to come to here because what happened? I received 1, 1, 1. Okay, sequence is already completed. Now I received 1. So this one should be counted for the new sequence. So I have to move to this one, not this one. You are right. I'm sorry. You understand? Because this one should be counted. This new one should be counted for the new sequence. That's why I have to come here to wait. Once you are in this state, that means you already have 1 in hand. You have 1. Once I come to this state, so I have 2 ones. Once I come to this state, now I have 3 ones. You got what I'm saying? Okay. But if you make it this way, as I said by mistake in the beginning, if you make this mistake, that means what should happen is after I receive 1, 1, 1, okay? So now I got 1, so I need to count for another 3 ones. You got what I'm saying? So by just changing the arrow, the behavior will be different. That's why it's interesting. You're right, I agree. This one has to move to. Okay. Anyway, so it's now I want to show you something now, guys. I'm gonna redesign the circuit again using melee. Okay, look how it works. So here I'm gonna design it using melee. As I told you, we have here 3 bits. Because it's 3 bits, that means I need 3 states. In case of melee, is that okay? Let's look at the 3 states and how it is different from the previous one. Hopefully you understand. Okay, so look here. In the very beginning, I have state 0, 0 here. This is again, I received 0 here. Okay. So if I receive 0 after that, so it has to be if I receive 0, the output is 0. So I didn't receive any ones yet. I didn't start counting yet. I didn't receive any ones. Makes sense? Okay. Now I receive 1. So I have to move to here. Okay. So once you come to this state, which is state number 1, I received 1, but still the output is 0 because I have only 1 in hand. 1 in hand now. Okay. Now, if I receive another 1 here, look here. So now I'm gonna move to this state. So now I have 2. I have 2 ones in hand. Okay. Okay. This is the difference between, listen, this is the difference between more and melee. In melee, if I receive another 1 here, I will go to the initial state again. So here, if I receive another 1, I will go to the initial state again, and then I will output 1. Okay. Let me complete it. So I don't need a new state here. This is the main difference. That's why in case of more, we have 4 states, but here we have 3 states. Let me finish your understanding. So here, I don't need a new state. I will let you know what. So now I have 2 ones, and I already received another 1 already. So that means I have already 3 ones. So I have to come back to the initial state again to start counting for another 3. Okay. Let's look for the zeros to complete it. So once you are here, you already have 1, and after the 1, I got 0. Okay, so now I have to go back to here, so it's 0, and then you have to output here 0. Makes sense? Okay, so now let's look at this one. If you are at 1, 0, and then after that, I received 0. Sorry, it's 1, 1, and then I received 0. Okay, so again, that means I have also to come to here. Here I have to, I received 0, and in this case, I have to output 0. I'm going to explain it again. what's really important here, you should understand what is the difference between mean and more. Okay, let me explain again. In the very beginning, I am here. Okay, once I receive 0, okay, I'm gonna just wait in this state when I receive 0. Okay, because I will start counting by ones when I receive 1, because my sequence is 1, 1, 1. Okay, once I receive 1, I will come to here. So when I come to this state, that means I already have 1. I secured 1. Okay. But what happens after this one? There are two cases. Maybe you are going to receive another 1. Maybe you are going to receive 0. If I receive 0, so I have to come back to the initial state again to look. So here I received 1 and then I received 0. So now I have to go to the initial again to look for 3 ones. Make sense? What if I receive another 1? So now I have 2 ones here. So once you come to this state, you have 2 ones. Is that okay? Once you have 2 ones, again, there are 2 possibilities. One possibility is I'm going to receive 0 after that, or I can receive 1. So if I receive 0, 1, 1, 0, we break the sequence. Okay, so that's why I have to go to the beginning again to start counting for 3 ones. I will go to the initial state again to start counting for 3 ones, and the output is 0 because I didn't fix the sequence. However, if I receive a 1 after 1, 1, I receive another 1, so that means that I already found the sequence. The sequence is already found, okay? And then I will move to this one to 0, 0 to start counting for another three ones. For sure, here there is no overlapping here. I'm not allowed overlap. Okay? If you want to allow overlaps, what should I do here? Instead, I can change this arrow. This arrow here, I can make it this way. Okay, 1 and 1. Okay, that means so that after 1, 1, okay, I got 1, so here I'm gonna output 1. Okay, then you got 1 again, you output 1. Very interesting. So the difference between either this one or this one. Okay, here in this one, if I go this way, there is no overlapping because again, this is the initial state. Once you come to here, you start over again. Okay, but here I allow overlap because I have 1, 1, and then I received 1. Okay, so I will look it here so that if I receive another 1, I will output 1. Receive another 1, you output 1. Very interesting. Just one arrow can control if there is overlapping or not. Okay, before I take question here, I want you to see, okay, the difference between this one and the previous one. Okay, look here, guys. This one is mean. Why? Because in the same state, 1, 0, the output can be 1 or the output can be 0. So the output does not only depend on the state, similar to unlike the previous case. That's why it has to be mealy. It cannot be more. Because the output does not only depend on the state. For the same state here, I can output 1 or output 0. Okay? To make it more, I have to add another, that's what I did here. To make it more, so that the output only depends on the state and not the input, I have to add one more state here. So what happened here, guys? Look, hopefully you understand this part. So now, once I come to this node here, I already have 2 ones. Is that okay? Look, I have received 2 1. Now I received another 1. I made another state for 1, 1, 1. A new state for 1, 1, 1. Here, I did not make a new state for 1, 1, 1. I just go to the beginning again to start again. Okay. But when you make a new state for 1, 1, 1, so here what happens here, always if you are in this state, the output has to be 1 most of the time. So the output does not depend on the state. It does not depend on the input. You can understand? Because I made a new state here. Okay. Again, this is the main difference. The main difference in case of more, I wanted the output to only depend on the state, not the input. In this case, to make sure this will happen, that means always, if I'm in this state, the output has to be 0 or 1. Always, as long as you are in state. Same thing here. Always, when you are in this state, the output should be 0. Always, when in this state, the output will be 0. Okay? So that's why I created a new state, so that always when I'm in this state, that means the output has to be 1. Anyway, if you don't know, understand this example very well. I have more examples to explain. Okay? Any questions? Okay. Again, the most difficult part again here is how to create the diagram. I'll give you more examples to understand better what I did. Now I will explain similar to what I did last time. Once you have the state diagram, how can you design the circuit? And this will be similar to what I explained last time. This is similar to what I have just explained. When the input here, if I'm in this state, the input is 0, I will stay in this state. But if the input is 1, I will move from here to here. Input is 1, I will move from. I'm just explaining it using some figures. Okay. So now let's come to the design. So here, similar to what I did last time, here I want to use as similar to what I did last time, guys. Here you have to put here the current state A and B. Okay, the current state, I have two flip-flops. I have one input. This one. Okay, so that's similar to what I did before. Now I'm explaining. Once you have the state diagram, how can you design the circuit? Okay. Okay. So number one, you have to put the states here. Now I have only two flip-flops, so I have A and B, two flip-flops, and then I have input X. Number two, again, this is similar to what I did last time. Number two, you have to put all possible cases here, similar to what we did before. 4 zeros, 4 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, 1 0, 1 0, similar to what we did before. Number three, you have to use your design to calculate the output here. The output has two parts actually here, the next state for A and B and the output Y. You got what I'm saying? So here you have to get this one from the figure. So let's see how can we make it. Again, it's similar to what I explained last time. If you see here the state is 0, which is state 0 here, okay, and the input was 0. Based on your design here, what should happen? What should happen when the state is 0 and input is 0? What should happen? Number one, I have to stay in state 0, that you see here, and the output has to be 0. Make sense? So here's this row is representing this error. So every row represents one error. That's similar to what I explained last time. Same thing here, if you look at the next state here. Okay, if I'm in state 0, 0, and then I have 1. Okay, so here I want to represent this arrow here. Okay, so the output here, the output is state 0. Okay, because the output here, as long as you're in state 0, the output always 0, and now I'm gonna move to state 1. Okay, same thing here. If I'm in state 1, here state 1 is here, and now I got 0. I got 0 here. So next state has to be 0, 0. Makes sense? And output is 0. Makes sense? This is similar to what we did last time. Then you have to finish to the end. Okay. So number one, you have, as I told you, number one, you have to put here states. You have input, put all possible cases here, and then you need to use this diagram to calculate the next state and the output. Makes sense? Now, next step, just steps. You need to decide which flip-flop you have to use. This is the next step. Assuming this time I want to use D flip-flop. Okay. Then after that, you need to design what circuit in order to, if this is the input, okay, how I need to design combinational circuit to guarantee I will get these two here. If this is the input, I will get this one. If this is the input, I will get this one. So I need to design combinational circuit. So as I told you last time, you need to find the input G, A, and GB. What input? If this is the present state, what should be the input? This is what the combination. This is the input of the combinational circuit. So I have a combinational circuit. This is the input of the combinational circuit. What should be the output of the combinational circuit to make sure this will happen in next state? You got what I'm saying? But here, because this is D flip-flop. D flip-flop, in case of D flip-flop, input should equal to the output. Make sense? Input should equal to the output. That's why I don't need to add one more column here. Why? Because if you add one more column, I will copy this one here and I will copy this one here. Very simple. So in the next step, if you want to get 0, so G has to be 0. In next step, if you want to get 0, then GS should be 0. You got what I'm saying? So I just instead, if you study the slide, you said maybe you are going to be a little bit confused because usually we have to make one column for the input of the flip-flop. Here, I don't need. Why? Actually, if you want to do it, that's okay, do it, but just waste of time because you are going to copy. If you need to get these values in the future, so this one has to be the input. So this actually output the new output and the old input. You got what I'm saying? So that's why here again. So after that, I need to find these are the inputs I have. I need to design. Look how it's simple. I want to design a combinational circuit. These are the input of the combinational circuit, and the output should be this one. This one, another combinational circuit for this one, another combinational circuit for this one. Okay, so that's what I did. So what I did here, the input here, we have. If you remember when I explained the key maps, I told you the first one A here, whatever you have here, A has to be here. This is A. The second one, whatever the name is, has to be here. And then the third one has to be here. Okay. And now, after that, you can see here, guys, this is numbers. Min term is 0, 1, 2, 3, 4, 5, 6. Sorry, 0, 1, 2, 3, 4, 5, 6, 7. So here I have to put 1 at 3, 1 at 5, 1 at 7. Is that okay? And then I can minimize it. I can take these two as one group. I can take these two as one group, and this is the output. So that means in order to make sure I will get these values, okay, I need to use this combinational circuit here. And this combinational circuit has to be the input of this combinational circuit is the present state and the input. Okay, if I do that, I will make sure I will get this value here. Okay. Same thing, repeat it again here. Here, for B, I need another combinational circuit for the flip-flop B. Again, this is min-term 0, 1, 2, 3, 4, 5, and 7. So here I put at 1, 5, 7. I make one group, another group, calculate it. Okay. For Y, here we have only one here and one here, which is number 6 and 7. So I put here 1 at 7 and 1 at 6, and then I found Y. Okay. So always Y here is actually Y here is actually equal A and B. So always here A and B should equal to 1. Okay. You can notice here, if it is 0, 0, I'm gonna get 0 because 0 and 0 is 0. 0, 1, I will get 0. So the only way to get 1 is when it is 1, 1 here. Okay. A and B. Okay. Well, so okay, that's it. Once you design it, I need to find this equation here, this one here, and this one. And then you can just connect it here. Okay. So you see here, this is GA equal to AX or BX. And then you can find this one here is actually GP actually should equal to GP should equal to AX or B prime X. Okay. I want to tell you something important, guys. In exams, in quizzes, you don't need the way this. I got this one from the textbook. The way we drew it in the textbook is just similar to the connection. How you connect it. Okay? To make it easy for me in grading, and also to make it easy for you when you do it, you don't need to have one X this way. Okay. Instead, you can make if you. Very important, okay, guys? I just want to make it easy for you. When you draw, you don't need to complicate this way. This is how you connect it, okay? But the way you have to do it, for example, you can tell me, okay, this is Y, and then you have here A and B. Okay, this should be enough. And then after that, when I have this is A and this is GA, and then here you can have here OR, and then you can have here N, you can have here N, and then you can repeat A again. B again, X again, X again. Okay. So when you repeat A multiple times and X multiple times, okay, you make the drawing much easier. You get what I'm saying? I know every A should be connected together using one line. I know that. Okay? So, and that's what you have to do when you implement the circuit. But when you do this way in exams, yeah, it will be easy for you this way and easy for me. Because sometimes it's really hard for me to just go behind the line to see what is A or B or whatever. Same thing for B here. You can say this is B, and the input here has to be. Also, I'm gonna make another pole this way. Have one N, and then you can here make AX, and then you can make here B prime X. Okay, that's more than enough if you make it this way. Separate this way. They are not separate, by the way. They look separate, but they are not. Why? Because A should be connected together, B should be connected together, X should be connected together. You understand what I'm saying? But there is no need to complicate this. Any questions? Okay. So now I will teach you, similar to what we did last time, how can I implement the same circuit using T flip-flop, for example. Instead of D, I want to do it using T flip. And that's what we did last time. So doing nothing here is new. Look here, guys, again, this is the input. And this is the output I need to get. Okay. Here. And then here you need, if you have it this way, and now you need to find the input. Here you need to add one column for the inputs of the flip-flops. You know what I'm saying? So let's see how we should it, similar to what we did before. How can you do it? Look here, guys. This is already you know how the flip-flop works. Very simple. If the current state is 0 and next state is 0, or the current state is 1 and then next state is 1, that means no change. That means no change. It means T has to be 1. This is the first case. Second case, if the current state is 0 and next time I want to make it 1, or if it is 1, next time I want to make it 0. So in this case, T here has to be 0, T here has to be 1. You got what I'm saying? So that's similar to what I did last time. So now let's design this one. Look here, guys. Here I am 0 in this state. I want to design a circuit so that next time I also get 0, no change. So if I want to do that, I have to make sure the combinational circuit I want to design, I have to make sure to give me 0 so that it is not change. Same thing here. This one is 0, and then it should be 0. So I'm gonna put here 0. Okay. Now it is 0, and next time I want to make it 1. So here the combination circuit has to put 1 at the flip-flop so that this happens next time. Next time it's gonna toggle. Okay. Same thing here. This one is 0, and this one is 0. Should be 0. This one is 1, and then I got 1. Should be 0. No change. 1 and then 1. No change. 0. 1 and 1. No change. 0. 1 and 0 should be 1 to toggle. You got what I'm saying? So here I designed it for A. You can design again for B. Same thing for B. Okay, guys? Again, in case of D flip-flop, if it is D flip-flop, I didn't because maybe this part will confuse you. You will find I added 2 columns. I will add more columns in case of T flip-flop or in case of JK, but when it came to D flip-flop, I didn't add. Actually, it should be there, but actually you will copy this one here, and also you will copy this one here. Okay? Because if I need to get 0, so I have to make sure this one is 0, because in case of D flip-flop, Q is equal to G. If I get here 0, I have to make sure this one is 0. If I want to get 1, I have to make sure T is 1, so that when the clock comes, I will see 1 in the output or in the state. Any questions? Okay, guys. Same thing. If I want to design it using JK flip-flop, it's exactly the same thing. But again, you need first you need to know. Look here, guys. If I'm 0, if the state is 0, and then next time I got 0, okay, what should be the values of G and K to achieve that? If it is 0 and next time I got 1, if it is 1 and next time I got 1, or if it is 1 next time I got 0, because these are the 4 possible cases. You need to know what value should be at G and K. What the combination circuit has to output for G and K to produce this one here. Okay, so let's see. Look here, guys. If the current state is 0 and next state is 0, remember how this can happen in JK flip-flop. How this can happen in JK flip-flop? 2 cases, not 1 case. 2 cases. For this to happen in either no change or reset. no change, JK means 0, 0. Reset means 1 and 0. So if JK equal any one of these two cases, so this transition from 0, 0 will happen. If I'm 0 and I want to go 0, so that means JK should be either no change or reset. Okay, so that's why here has to be 0 here and has to be X here. X means it doesn't matter because if this one is 0, no change, and then I will move from 0 to 0. But if this one is 1, I will make a reset, and then also I will move from 0 to 0. You can understand? Okay. This is number 1. Number 2, if the current state is 0, but next one has to be 1. This should happen in 1 or 2 cases in JK flip-flop. 1 or 2 cases. 2. Which are 2? Which 2? Yeah, set and toggle. Yes, because you can toggle. Toggle means 1, 1. Set means 1 and 0. That's why here I say here it's 1, here X, whatever you have here. Because if this one is 0, you set, and I will get 1. Or if this one is actually 1, I toggle. Okay. Same thing here. If I am 1 and I want to go to 0. So this again should happen in 2 cases, either toggle or reset. Toggle means 1, 1. Reset means 0, 1. That's why here I said whatever you have, it doesn't matter. Okay, this transition will happen from 1 to 0. Same thing, if I am 1 and next time I will be 1, okay, so this should happen in 2 cases, either no change with 0, 0, no change, or actually it should happen at set. Set means 1, 0. This is J and K. So here it doesn't matter what is the value of K, that's why I made it X. Make sense, guys? And what is the meaning of X? It means don't care. So when you design, when you make the key maps, this will be don't care. Okay. So now I will make this table here, guys. Okay, look here, guys. This is the input, this is the current state, and this is the next state. So again, now A is 0. Next time I want it to stay 0. The combinational circuit for GA and KA for flip-flop A. What should be the output of this combinational circuit to make sure when the current is still 0, next state also I will get 0. Okay, so you can see here 0, 0 here, guys, means 0x. That's why I'm gonna put here 0x. I think I have a nice animation. Look at the next animation. Look here, guys, 0, and then next time I want to make sure it is 0. Again, I'm designing A flip-flop. I need to repeat again for B flip-flop, okay, to make this part here. So, but let's start with A flip-flop, okay? So here I am 0, next time I want to make 0, so in this case, GK should be 0x. This transition from 0 to 0 should happen when GK is 0x. Next, okay? Now I move to the next one. From 0 to 0, same thing, 0x. Okay, let's move to, from 0 to 1. If I want to move from 0 to 1, okay, you can tell from this table from 0 to 1 tend to be 1x, and so on. All the way until you come to here. 1 and 0. So now it has to be from 1 to 0, it has to be x0. Sorry, x1. Makes sense? This is for A. You need to repeat again for B. Okay, guys? Because this is the current state, this is the new state. And I wanna, who's gonna move, who's gonna make this transition? Okay, from the current state to the new state. It's a combination circuit. I need to design a combination circuit so that when it puts some inputs, and this as a flip-flop, the flip-flop is gonna move from this state to this state. You can understand? That's why I'm designing it this way. Okay. Once you have here this one, similar. So now I need key maps for GA, I need key maps for KA, I need key maps for GB, another key maps here, and in this key maps we have don't care, what a lot of don't here. Here I'm explaining again, you have to put it for B. So 0, 0, you have to put 0x here, 0, 1, you have to put 1x here, and so on. 1, 0, you have to put x1 here, okay? And now, again, you have here, I need to make key map for this one, GA here, okay? This GA has to be functioning in the current state and input X we have, okay? Again, you can see we have a lot of don't care. This will help it to simplify. So this is GA has to be this way. Same thing for PA, okay? So here we have don't care. So I'm gonna take this one like one group. GB here, I'm gonna take all of this as one group. Here, I'm gonna take this one with this one here, these two together this way. Okay, guys, any questions? Again, to me, this is, and then just you make your design here. Okay? Any questions? Okay, let's have more examples just to understand better because again, to me, the difficult part is how can you create the state diagram. And you see, it's very interesting. Just when you change one arrow, but it will be different, right? Because every arrow you make in the state diagram, this is how the circuit is going to behave. You're not designing it. You got what I'm saying? So that's why if the state diagram is wrong, so for sure the sequence will be wrong. Sure. Okay. So let's say I give you more examples here. Here, I want to design a sequence to detect 101. 101. Again, I want to make it using Moore. Also, I want to make it using Mealy. Okay. Look at the difference. When I design it using Moore, I have to make sure for every state, every state has a unique output. And because to make sure of that, I will add one more state as you will see right now. Okay, but here in case of Mealy, 3 states should be enough. 3 states, okay? Because this state here, this state can have 2 different outputs. It can have one here, or it can have 0 from the same state. Okay, Mealy. Anyway, so let's start with the first one. And you already know if the sequence is 3 bits, 3 bits. So that means in case of Moore, you need 4 states. But in case of Mealy, you need 3 states. You already know. Okay, let's do it. Very easy. Look here, guys. I want to look for 101. I have initial state here. So initially, I'm here. Let me use a different color. Initially, I am here. And as long as you are in this state, the output is 0. Okay, initially, I'm here. Okay, so in the very beginning, what happens? There are 2 possible cases in the very beginning. Either I receive 0 or I receive 1. If I receive 0, so I have to look here, come to look here. Why? Because I'm looking for 1. Because my sequence starts by 1. So if I receive 0, you have to wait in the initial. I'm not gonna start counting, okay? Okay, now, so that's why I'm gonna, what if you receive another 0? Okay, you are gonna continue to stay here. So if I receive 0, 0, 0, 0, you are gonna stay in this, you are gonna wait here in this state. Make sense? Okay, now, what if I receive completely this sequence? What will happen? Completely this sequence. Okay, number 1, when I receive 1, this is the first one here. I will move from this state to this state. Then, when I receive 0, this 0 here is going to move me from this state to this state. Okay. Now, when I receive 1, I will make one special I will make one state for the complete sequence when it is 1, 0. Okay. So you can see if I start with, if I receive 1 and then 0 and then 1, I will move all the way until I come here. Make sense? So if I come to this state, what it means? It means my history. I'm repeating it because history is very important in sequential circuits. Combinational circuits don't have history. Okay? Now you have history. History means if I'm in this state, so my history was 1, 0, 1. Make sense? To come to it. So once I come to it, it has to be 1, 0, 1. Every time I come to here, the output always has to be 1. So the output only depends on your state because I made one special state for 1, 0, 1. Here, I'm not gonna make one special state for 1, 0, 1. Instead, once I have 1, 0, once I receive 1, okay, as we see here, the output will be 1. And then I can decide if there is overlap or not, I can come here or come here. Or if after 1, 0, if I receive 0, so the sequence is broken, so I will come to here and then the output is 0. I'm not going to make one special one state for 1, 0, 1. And so that's why there is one state difference between Moore and Mealy. Okay. Anyway, so let's again. So if I come to here, guys, that means I already have 1. I received 1. Is that okay? It may happen after I receive 1. There are 2 cases. Maybe I'm going to receive 0 or 1. Make sense? What happens after 1? I receive 1. What should happen? Another 1 after 1. Should I go back to here again? Or I can consider this one the first bit for the sequence. That's why I have to go back to here. Yeah, here you have to go to. See what I did? So again, every time, again, if I have one, and then I receive one, so I have to wait here in this state because I really have, I execute one bit, it's still one bit. Then you receive one, I have to stay here. You receive one, I have to wait here. Because the last bit here, this is, you should not go back to here, because if you go back to here, I need to look for another one. I only have one, you got what I'm saying? So here's that's why you can see here. If I receive one, and then I receive another one, I have to look to here. Make sense? Okay, let's see. What if you receive 0? So now I have 1 and then I receive 0. So I'm gonna come to this state here, 1, 0. Okay. Same thing. When I come to this state, there are two possible cases. I may receive 0 or I may receive 1. Think about it. If I receive 0, you already, the sequence is broken because it has to be 1, 0, 1. Okay. So that's why I have to go to the beginning again to start looking for new sequence, 1, 0, 1. Makes sense? You broke the sequence, okay? So that's why if I'm already 1, 0 and I receive 1, that's only 0, the sequence is broken, so I have to go back in order to look for 1. Okay? But now, if it is 1, 0, and then I receive 1, oh, I'm happy. 1, 0, 1. Okay, so I will come to this state here. So once I'm in this state, the output should be 1. This is the winning state. Okay? So here it has to be 1, because I really exceed the sequence 1, 0. Make sense? Now let's come to the interesting part, okay? So now I received 1, 0, 1. I'm happy. Now what should happen after that? Then maybe I'm gonna receive 0, or maybe I'm gonna receive 1. Make sense? Let's see. If I receive, now there are two possible cases. Do you allow overlapping or not? Overlapping means 1, 0, 1. Do you want to receive another 1, 0, 1 to generate 1? Or it's okay for you to overlap this one. That means 1, 0, 1, I'm going to output 1. And then 0, 1, I will output 1. Because this one overlap between the two sequences. Very interesting. Just one arrow can decide. Okay. So now I can see here, I can do here, I can say, okay, if I allow overlapping, that means after I receive 0, so now I have 1, 0. Okay, so yeah, so now I have 1, 0, so I need to look for only 1. That's why I'm gonna move to allow overlap. So if I already have 1, 0, 1, and then I got 0, so now from the sequence I have 1, 0. So I will come to here because I have 1, 0. So I'm waiting for only 1. If you receive after that 1, I will come to here to output 1 again. Now you allow overlapping. But if you don't allow overlapping, instead of this one here, you have to come to the beginning again. Here, no overlapping. So that after 1, 0, 1, I will go to the beginning again to start for 1, 0, 1. This is the initial state. Every time you come here, you are going to start over again. Once you have here, so you have partial part of the sequence. Once you have here, you have 1, 0. Because it's very interesting. So now I already have 1, 0, 1. Okay? If I want to start over again, to look for 1, 0, 1 to give output here and output here, that means there is no overlap. That means I have to come. Instead, again, either this one or this one should be one of them. That's why I'm making this one, this line is broken. Okay, either one of them. Or if 1, 0, 1, I can consider this one as a part of the two sequences. So now I'm looking for, and then once I receive 0, that means I already have 1, 0, and then I need to look for 1. This is the state of 1, 0. So I'm going to come to here, so that now I have 1, 0. Any questions? The last one here for Mealy. For Mealy, it's almost the same thing, guys. The only difference that you see here, when here when it is 0, once I receive 1, I will come to here. 1, 0, I will come to here. So it's almost the same thing, but the difference here, instead of making one more stage, okay, no, everything will be done here in this state. So let's see how it works here. This is an important one. Look here. So now I have 1, 0. Okay. Now there are two cases. One case is if I receive another 0. So now the sequence is broken, I have to start over again, because that's what I did. Make sense? Now, I have 1 0, and then I received 1. Number one, the out has to be 1. For sure. 1 0 1. The out has to be 1. But do you want to allow overlapping or not? No overlapping, so I have to come to the beginning again. I will output 1, but I will come to the initial state again to look for 1 0 1. If you allow overlapping, okay, after you receive here 1, yeah, sorry. So you already have 0 1 here. Okay, so after I received 1, I already have 0 1. So that's why I will move to this state here because I already have 1, so that next time when I receive 0, I will come to here in the side again. Okay, so again, it depends on, so once you receive 1 0, now there are 1 possible cases, and then I receive 1. Okay, so in both cases I have to output 1 because I have already received the sequence. But now overlapping or not, it depends on should I go to the initial state to look for another 1 0 1, or you are gonna come to here because you already have 1 and you want to build with this 1. You want to take this 1 as a part of the new sequence. Make sense? Anyway, I think we don't have time, but I give you one more example. I will explain next time 1 0 0 1. Okay, that's what we have. Okay, thanks. So let's take the attendance quickly. I think this sequential